So welcome everybody to today's seminar. It's a pleasure to have with us the first, but not the last, Italian scientist which will present his research. Dr. Francesco Pineider is a close friend of mine. Close friend, it means that we went through high school and university together. So we have a strong connection, strong bond. But this is not the reason I invited him to present here, to give a lecture about plasmonic and active plasmonics. The reason I invited him here is his outstanding track record, his outstanding curriculum. He graduated in 2000. He obtained his PhD in 2009. In the same group I did, in the University of Florence under the supervision of Professor Roberta Sessoli. During his PhD, he investigated thin films of molecular magnets on solid supports. After this, he changed his research interests and he moved to investigate plasmonic materials. That's the reason I invited him here. And in this new for him at the time research field, he got very good results in terms of number and quality of publications. Okay, so he provided me a short CV for the divulgation of the present seminar, where he states that he's author of over 50 papers and 40 oral contributions to national and international conferences. This is not, I believe he could have put more striking results. He obtained several prizes for his research activity, and he is now professor at the chemistry department of the University of Pisa in Italy. Yeah, and he will talk to us about. I asked him to introduce the plasmonics. What's plasmonics? Because I feel that plasmonics is a very active scientific field at the moment in chemistry, in physics. He's a chemist, so he will talk about from the chemical point of view, but I asked him to introduce the topic for all of us, including me, who doesn't know nothing about it. Yeah? Then he will show us some fields of applications of the topics, and then he will show us his research results. He's involved in controlling the plasmonic properties of nanosystems with magnetic field, mainly. So I hope not to have forgotten anything. And please, Francesco, as we say, the floor is yours.
Okay, thank you, Giordano, for this very kind introduction. So it's my pleasure to be here, and as Giordano mentioned, we're very good friends, and I also know the chemistry department of UFR Jota, so I'm not there physically, but I kind of it kind of feels like if I were there actually. So it's a double pleasure for me to be here today talking to you about plasmonics and a little bit of my research areas and fields. So yes, I work at the Department of Chemistry and Industrial Chemistry of the University of Pisa. I'm an associate professor there, so I have a nice research environment, and I must say this, I have to apologize because I forgot to prepare an acknowledgements slide. So I'm just going to tell you straight away to acknowledge the people from my group and my department and other people around Europe that work with me. So most of the work I'm going to be presenting that comes from our group has been carried out by Dr. Elvira Fantechi, Dr. Alessio Gabbani, and Dr. Gaia Petrucci, together with who have been postdocs or are PhD students in my group. And currently their work is being carried on by younger generations, Ananta Krishnan Mon, who just started the PhD, and several very talented students, bachelor and master students, Marco Tomaiolo, who started synthesizing some of the things I'm going to present you, Marina Ruggeri, who also worked a lot on these systems I'm going to talk to you about. Okay, so let's start. And as Giordano mentioned, I'm going to start from the beginning, because I'm going to present you a few basic concepts about plasmonics, which could be useful for those of you who are not familiar with what is a plasmon resonance. So this is how the today's seminar looks like. We're going to introduce plasmonics, say what it is, and what are the critical parameters that influence it. But then we're going to delve into what's the interest of plasmonics in today's research community and potential impact on society. That means applications, both current, so already demonstrated, and prospective, so those that are a bit more visionary, that might be tomorrow's applications. And finally, I'm going to get into something a bit more specific, but in my opinion, very interesting, the opportunity of controlling actively plasmon resonance. So basically controlling the optical properties of matter through different stimuli, okay? So this is active plasmonics. I'm going to try to give you an idea of why it's interesting, and then give you a very brief overview of what can be done to modulate plasmons. Okay, so plasmons. So this slide starts with, let's say, kind of definitions. They're not really strict definitions. First of all, what's a plasmon? So plasmon, as everything in science that ends with "on," it comes from physics, and it's a fundamental unit of something, electron, photon, you know. Plasmon is basically a collective oscillation of charges, mostly electrons, and the plasmon is the basic excitation of this kind of oscillation. So I keep this slide usually for Italian audiences, because every Italian person grew up with these kind of biscuits. Of course, they're just in Italy, but they're called plasmon, and so these are Italians are all fed with plasmon since they were born. Okay. Oh, I know it doesn't work in other places, but I had to leave it. So surface plasmons are a bit more, let's go into more specific things. And so the surface plasmons are this oscillation of charges between the metal that contains the charges, the electrons, and another medium, which is usually, it's always an insulator. Okay, so surface plasmons are these oscillations that happen between a metal and an insulator, and this is what we really are going to talk about. And plasmonics, of course, is the term that describes all the studies basics of plasmonics or of plasmon resonances and how they can be used for applications. Okay, so plasmons come in different flavors, and they basically depend on the dimensionality of the metal that supports it. What do I mean by dimensionality? I mean that if we take a piece of metal, let's say a piece of gold, macroscopic one, this is a three-dimensional object. Okay, it is macroscopic in all three directions. But if we start slicing away one direction at a time, we get to two-dimensional materials, one-dimensional materials, and zero-dimensional materials. Okay, so we basically go from a bulk material to a thin film, or to let's say a rod, or to a nanoparticle, nanosphere, whatever. Okay, so in this case, slicing the material means reducing its size to roughly 10 to 100 nanometers. Okay, so in plasmonics, the concept of small is it can be identified within this size range. Okay, so if we want to talk about a two-dimensional plasmonic system, it's basically a film which is infinite in two directions, and about between 10 and 100 nanometers in another direction. Okay, so this is what I mean by dimensionality in plasmonics. And according to dimensionalities, we can have several types of plasmons. Volume plasmons, these are really not interesting for us because these are oscillations that cannot be excited by light. So let's leave them alone for now. We have propagating plasmons, which are very important. These are, we will see this better in a few slides. These are kind of waves that propagate between the top of the metal and the insulating layer. Then we have localized plasmons, and these are going to be the focus of this talk. In this case, we have charges that oscillate around the nucleus of the core of the nanoparticle. Okay, between propagating plasmons and localized plasmons, there is this funny no man's land, which is the 1D systems in which you can have localized plasmons or propagating plasmons according to the direction you take into account. But this is not really something we're going to cover, so let's go on. So let's take a nanoparticle. Let's take a gold nanoparticle, for instance, which is probably the most well-known plasmonic substrate, at least for chemists. And this is, I'm going to give you here a very, very rough picture of what happens. So I apologize for being so visual, okay? But so when you shine light on a gold nanoparticle, you have the electric field of light. It oscillates, of course. These oscillations, so this electric field drives a coherent motion of conduction electrons in the nanoparticle, and these all the conduction electrons oscillate together, and this results in the absorption of the electromagnetic field of light by the nanoparticle. And of course, as you know, when you have absorption, you have a peak. So light does not propagate anymore, it's absorbed, and you have a peak, and this is called the plasmon resonance peak. Okay, so basically plasmonic materials have this property of absorbing or scattering light at a certain wavelength where you have the resonance. So this actually has been used since antiquity. Of course, who designed this Lycurgus cup didn't know about plasmonics, but he accidentally fabricated nanoparticles in this kind of glass, ceramic glass. And you can see that this is stored at the British Institute in London. This is a very, very famous picture for plasmonics. You can see here that if you shine light through this artifact or grazing incidence light, you get different responses. And this corresponds to absorption to the right and scattering to the left of light caused by nanoparticles. So this is very fancy, used to be a very fancy object for antiquity. Bright colors also in cathedral windows are sometimes due to dispersion of gold or silver nanoparticles in the glass. So these have been used since antiquity or ancient times, but of course the scientific journey of plasmonics is of course much younger, and it all started at the beginning of last century when there was an observation by a scientist named Wood who observed very strange behaviors from metallic gratings, and he really could not understand why these metallic gratings behave like this, and he called them anomalies. And later on, these anomalies were rationalized as surface plasmon resonances. And since then, basically since the second half of last century, several theoretical and experimental works came out, and plasmonics started its time, let's say its heyday, okay, since the beginning of the 2000s. As you can see here from these number of citations of papers containing the word plasmonics. And as you can see, it's very heterogeneous. Not just chemists and physicists are interested in plasmonics, but many other scientists. And I think you will understand why when I tell you about the applications of plasmonics. So let's give this brief overview of what are the key parameters that influence plasmon resonance. That means what influences the position of the plasmon resonance and its intensity. Okay. Most of these observations can be rationalized using this very old model by Gustav Mie. It's called the Mie model, the Mie theory from the beginning of last century, 1908. And it's a very elegant one because Gustav Mie just solved the Maxwell equations using specific boundary conditions, meaning that he took a sphere and he said, okay, inside the sphere we have a metal, outside we have an insulator. And just solving the Maxwell equation, he was able to predict most of the plasmonic properties of spheres of any size, of any material. So there are basically four, but one is out of the Mie model. Three main parameters that govern the plasmonic properties. The first one, and the most important, is the composition of the metal, so of the plasmonic particle. Okay, so which metal constitutes the plasmonic nanosphere. Okay, and as you can see, this is all theory, but it tells this tells you that, for instance, magnesium as a metal would be a very good plasmonic material in the ultraviolet. Lithium would be nice in the visible, but of course you know that it's basically impossible to prepare a stable metallic lithium nanoparticle. So this is mostly speculation. It's interesting to see here gold, and in fact gold is a very important plasmonic material, but we'll come back to that. Another very important thing, and this is something we will discuss a bit more in detail, is that the the refractive index of the insulator, so it's called here the matrix, surrounding the metallic nanoparticle, has a strong influence on the position of the plasmon resonance. And this is very important for sensing biomolecules or big molecules. It's called refractometric sensing, and basically it relies on this, that the optical properties of plasmon resonance depend on the refractive index of the medium. So we'll see how this works. Finally, there's a dependence also on size, on the optical properties of nanoparticles. This is not as important and as it is usually said, but in fact it does have an influence. We will just skip this because it's not interesting for us right now. But do know that you can have resonances of several types of order: dipolar, quadrupolar, octupolar. So there is some size dependence in plasmonics. On the other hand, now we will focus on what is usually most interesting for chemists, which is small nanoparticles. Small plasmonic nanoparticles can be treated in with a very simple model that comes from me theory, but it's an approximation. It's called dipolar approximation. So first of all, let's say what does small mean? Small means that the size of the particle is small compared to the wavelength of light that interacts with it. Usually we take factor 10 to be a good indication of small. So for instance, if we take light in the visible, let's say 500 nanometers, a gold particle will be small if it's smaller than 50 nanometers. Okay, so this is what I mean by small. In this case, it is reasonable to consider that the particles behave just as dipoles, so they oscillate just as a dipole. So you have just one peak, the one I showed you before. And this works just for, there's a certain number of constraints to this model, but most are usually met. So this is a very, very well-known model. And the key information here comes from this equation. This tells you the extinction cross-section of a nanoparticle, of a small plasmonic nanoparticle. What's an extinction cross-section? It's basically the extinction coefficient of the nanoparticle, of a single nanoparticle. And as you can see, okay, so these are all parameters. I'm going to try and give you a quick overview of them, but there are basically three very important parameters here. Epsilon 1, epsilon 2, and epsilon m. So epsilon 1 and epsilon 2 are called the real and the imaginary part of the dielectric function. And they basically describe the optical response of a material, or in this case of the metal. Epsilon 1 is related to the refractive index of the material, and epsilon 2 to its absorption, so to its extinction coefficient. Okay, so these two together describe the metal, and epsilon m is the dielectric constant of the solvent or of the medium. Okay, it is usually just a constant because it does not change very much with wavelength, and it's a real quantity because it does not, it has only the real part, because the solvents usually do not absorb, so they don't have any extinction in the visible. Okay, so the very important part of this equation is this fraction here, and as you can see, there is a point here in which you can have zero, because the signs of epsilon 1 and epsilon m are usually opposite. So that means that there is a wavelength at which this term here will be zero, and you will be left with epsilon 2 here, epsilon 2 squared here. So this means 1 over epsilon 2. And this tells you that at a certain wavelength, determined by epsilon 1 and epsilon m, you have the function that tends to infinite, okay? And it does not go to infinite because it has an epsilon 2, which is, it must be as small as possible, but is never zero. So you have a peak here with a finite height, okay? And this equation is important. Why? Well, because in refractometric sensing, this is really where it all comes from. Epsilon m is referred to the refractive index of your solvent, of your medium. So if you change this, you will automatically change the resonance condition of the plasmonic nanoparticles. And this is why we have this refractive index dependence. So as you can see here, this is a silver nanostructure in air or in different solvents. Okay, it's not very easy to read, but methanol, propanol, chloroform, and benzene. So with increasing refractive index, and you have the peak that moves to the red as the refractive index increases, and you see that there's roughly a linear relation between the wavelength of the peak and the refractive index of the medium. So of course this is can be very interesting, and I will show you in a few slides how this has been used and proposed. Finally, let me spend another word on this epsilon 2, so how much the metal absorbs light. This is really one of the critical points that defines which metal is a good plasmonic metal or a bad plasmonic metal. So I hope that it's clear to you that this must be, from what I said right now, that this epsilon 2 must be as small as possible at the resonance condition, okay? And you can see here the comparison between silver and gold, which are two good plasmonic metals. But you can see here that silver is slightly better. Why? Because a silver nanoparticle has a resonance at roughly 400 nanometers in the dipolar approximation. And you see that here you have no absorption coming from interband transition. The interband transitions are the transition between the D bands and the S bands. On the other hand, in gold, you do have some overlap between plasmon resonance and interband transition. This means that at the resonance, epsilon 2 is bigger for gold than for silver, okay? So silver gives more sharp peaks, more intense peaks than gold. So in principle, on paper, it's a better plasmonic material. Then silver is more easily oxidized, is more difficult to prepare. So for several reasons, gold is the leading plasmonic material by far. But this is for practical reason. If we didn't have to take into account chemistry, silver would be better. Okay. Okay. So finally, I'm going to introduce you to a very interesting and unexpected, from my point of view, class of materials that can be plasmonic, and these are heavily doped semiconductors. Okay, what does it mean? Let me skip to the next slide. Okay, no, sorry, I don't have that graph. Okay, what does it mean? You have a semiconductor is a material in which you have a band, a low energy band, which is full, and then you have a band gap and a conduction band, which is empty. Okay, so if you can populate the conduction band, you can have some kind of conduction. Okay, that's why they're called semiconductors. If you are able to, with a dopant, to introduce a significant amount of electrons in the empty conduction band, you have a material that behaves like a metal, but it's going to have less electrons per unit volume. Okay, you can see here what I mean. A typical metal has this rather huge number of electrons per cubic centimeter, 10 to the 23rd. Doped semiconductors can be, so the density of electrons can be to some extent controlled by changing the doping, but typically you are more or less in this ballpark, 10 to the 20 electrons per cubic centimeter. Actually, the most famous heavily doped semiconductor is something that we all use every day, which is indium tin oxide, or ITO. This is a transparent conductor that is found in all touch screens. You know, touch screens are capacitive devices, so when you touch, you basically close a circuit, and so you need something that is conductive, but also transparent. Otherwise, you wouldn't see the screen. So all our screens contain these doped semiconductors. Why am I talking about electron density? Well, because the position of the plasmon resonance directly depends on the electron density. So the more electrons you have per unit volume, the more the plasmon will shift to the blue. If you have less electrons per unit volume, you will move to the infrared. And as you can roughly see here in this graph, if you move from 10 to the 23rd of metals and the visible to lower densities of electrons, you can have plasmons in the near infrared, mid, far infrared, all the way down to terahertz and microwave. Okay, so this is a very, very powerful concept. Okay, you can move your plasmon resonance around without worrying about size, shape, whatever, but just by using a semiconductor and doping it to the level that you require to have a plasmon resonance where you like. Okay, very powerful. Okay, I'm making it a little bit more easy than it is in fact, but the concept is valid throughout the electromagnetic spectrum. Okay, so this is a very important class of plasmonic materials on which there is a lot of interest and a lot of developments in these years. Finally, the last key parameter for controlling plasmon resonance is the shape. Okay, so remember, it's more important to change the shape than the size of a plasmonic particle if you want to move the plasmon resonance around. Okay, or change material. Okay. So the most important kind of anisotropic nanoparticle that can be prepared by chemistry are the gold nanorods. You can prepare very nice nanorod ensembles. And here the very important thing is that you have two modes that can be excited by light. And one is the longitudinal mode, so along the long axis of the nanorod. And the other is the transversal mode, so along the short direction, okay? This means that an ensemble of gold nanorods will have two plasmon resonances if they are free to move in solution. And you can see these spectra, they show you that you have one plasmon resonance here and another one here. And what happens is that the second plasmon resonance, the one shifted to the red, can be tuned over a wide range of wavelengths by changing the aspect ratio of the rod. Okay, so if you have a rod with always the same diameter and you increase the length, then you will shift the second red, the longitudinal mode, towards the infrared. Okay, very powerful tool to control plasmon resonance position. Okay. As I told you, this part is not covered by the Me theory, but it's fairly well described by an extension of the theory, which is called Gans theory. And this approximates anisotropic objects as spheroids, both oblate or prolate. So in the case of the gold nanorods, you would approximate them to a very elongated rugby ball. Okay. Okay, the final concept final general concept about plasmonics is that shape is also very important to control how light is redistributed around the nanostructure. So far, we just said that light is absorbed, okay, by the nanostructure. But in fact, as plasma resonators become bigger, they also scatter light, and they concentrate light in the near field, so just around the nanoparticle in specific points, okay? These are called hotspots. This is a simulation that just tells us how light is redistributed around a plasmonic nano resonator, okay? So if you take a sphere, you have that, and light here is horizontally polarized, so it oscillates like this. It comes from above the screen and goes into the screen, or vice versa, but the polarization of light is horizontal, and you see that light is concentrated at the edges of the nanoparticle, okay? Notice the factor with which the hotspot concentrates light. It's about 10 in this case, but if you take a sharp object, charges, oscillating charges will concentrate on the tip, okay? As you can see here, if you take a prism, for instance, with a triangular base, you get higher concentration at the tip. This is called the antenna effect, and can be very, very important to obtain strong electric field enhancement in specific points of the nanostructures. And this is very important for field-enhanced spectroscopies, which is one of the most important applications that I will show you in a few minutes, okay? The antenna effect is called like this because it's basically this very, very similar. I would say it's the same effect as with minor modifications to what regular antennas do. This is a very elegant thing about electromagnetism, that it scales very well with size and frequency. So take regular antennas, you know, they're the ones that are used to get radio signals or video signals. They're typically, let's say, of the order of 1 meter, okay? And they must interact with what? With radio waves, which are of the order of a few meters, okay? If you take a gold or silver nanorod, nano antenna, let's call it, it has to interact with visible light. So its wavelength is around 1 micron, okay, 500 nanometers, and its size is of a few tens of nanometers, okay? So you can see the analogy between classical antennas that interact with electromagnetic field of bigger wavelength and optical nano antennas that interact with light, which has a smaller wavelength, okay? Okay, so let's go on. So this part was a bit more concept, full of concepts, but now we'll see the applications, okay? So this is a bit more relaxed part. So the first important application is, as I told you before, chemical or biochemical sensing based on changes in refractive index. So the state of the art of refractometric sensing based on plasmons relies on propagating plasmons. So you need a thin film of gold, for instance, and a device to excite this propagating plasmon, which is, it requires a prism. I will not go into details, but it's a bit bulky, and it works like this. You shine light at a certain angle on the gold surface. At a certain angle and at a certain wavelength, you will excite the propagating plasmon, and so light will not be reflected anymore off the surface, but will be absorbed and used to excite the plasmon. So if you take a reflectogram at fixed wavelength as a function of the incidence angle of light, you will see a dip in which most of the exciting light is absorbed, so you have zero reflectance. Okay, so this resonant condition is the same thing as the resonant conditions for nanoparticles, in which you have a peak. Here you have a dip in reflectance for the gold nanodisk. Okay, this is the working principle. So how does it work? How do we make this work as a sensor? Well, basically, you have to take the gold surface, functionalize it with some receptor, okay, so some small molecule, which will be able to selectively bind to a big molecule like a protein. Okay, so once it binds, the refractive index around the gold, let's say close to the gold surface, is going to increase, because of course water has a certain refractive index, but more organic molecules have a higher refractive index. Okay, this means that if the medium changes refractive index, also the resonance conditions will change, and so the dip in reflectance will shift to a different angle or a different wavelength. Okay, and so this is how it works. You have your functionalized surface. This is gold. This is where the plasma resonance occurs, and this is a laser, and this is a detector, and an angle scan will be done, and you'll get this kind of reflectogram. Okay, once the molecule bind, the refractive index changes, and the whole reflectance spectrum will shift. Okay, so you can just choose to work at a fixed angle and just look at how the reflectance changes. If you are here, okay, and you see and the resonance conditions change, you will change your reflectance from 50% to nearly 100%. Okay, if you stay fixed at this angle. Okay, so this is called a sensogram, and this is the state of the art. There are commercial devices that work like this. So what we want to do is to replace those sensors based on propagating plasmons with nanostructures, nanoparticles that do the same. Okay, there are several advantages. You can use much simpler instrumentation. You don't need all these moving parts of angle scanning and all that. A very simple spectrometer will do. And there are also more interesting advantages. For instance, you can do single particle experiments. So this is a bit, I won't go into details, but this is a very, very nice experiment in which these scientists tracked the plasma resonance position of one single couple of nanorods, okay, so 2 nanorods, and they changed the distance between the 2 nanorods by making a DNA strand shrink or expand, and they saw this change of plasma resonance position with just one couple of nanoparticles. Very nice. And you can also do multiplexing, so you can prepare several wells in which you have nanoparticles, and in each one you can place different analytes, and so in just one shot you get a full screening of samples against several antibodies, and you can do this can become very, very powerful. Okay. The other thing which is very important for plasmonics is field enhanced spectroscopies. Okay, so I think that at least some of you are familiar with SERS, surface enhanced Raman scattering. This is because it's the most successful field enhanced spectroscopy. Then there are others. I will tell you something about each of them, but let's start with field enhanced, surface enhanced Raman scattering. So as you all know, Raman scattering is a very nice spectroscopic technique on paper, because it allows us to have very important fingerprint information on molecules. And in principle, it's very convenient, because you just need a laser and a detector, Yeah, and a monochromator, of course, but you can do analysis in situ without destroying anything. You just need to, get to the surface of your sample and analyze it, and you'll have a rather good set of information on the chemical composition of the sample. The drawback is that the cross section of Raman scattering is very, very low. Okay, so it's a process that is not at all the most has a high probability, because when you shine light on anything, you have scattering which is mostly elastic, so at the same wavelength as the incoming light, and then you have small intensities of inelastic scattering, which is what Raman works on. Okay, but this has been found to be much improved by using substrates that are plasmonic. Okay, in this case, let's put it in a simple way. Since a scattering process involves interaction between light and matter twice, this means that the intensity of the Raman signal will scale to the power of 4 compared to the with respect to the intensity of the electric field of light that touches the sample. Okay, so this alone makes field enhancement very, very relevant. Okay, and as you can see, there are several types of substrates that have been proposed to increase drastically the Raman signal through plasmonics. Simple spheres, and you have to put your molecule on the surface of the sphere, or arrays, rather disordered arrays of gold or silver nanoparticle, or just rough gold surfaces. Okay, a rough surface has some edges and bumps that will locally support Plasmon resonance. So this is enough to increase by orders of magnitude the intensity of Raman signal. You have a rough gold surface, you place the molecules you want to study on the gold surface, shine light, and you get these orders of magnitude of increase in the Raman signal. Okay, so Raman is also very lucky case, because there are other mechanisms that concur to this enhancement. In general, though, all other spectroscopies are based on a common phenomenon. Field enhanced spectroscopies, sorry. So spectroscopies that are amplified by plasmon resonance. So it all starts with surface enhanced absorption. Okay, so if you can concentrate light in the vicinity of the nanostructure, if a molecule sits close to the plasmonic nanostructure, this will absorb more light than without the plasmonic nanostructure. So surface enhanced absorption then can lead to several other Plasmon enhanced phenomena. Surface enhanced infrared absorption. Okay, I'll show you a picture of this in a moment. Surface enhanced fluorescence, circular dichroism, magnetic circular dichroism, or strong coupling phenomena. So all these effects and surface enhanced spectroscopies start from an increased absorption of light by molecules close to the plasmonic system. So infrared absorption works like this. You need a plasmonic system that has a plasmon resonance in the infrared, okay, where infrared transitions occur. And for this, you can take heavily doped semiconductors that work like a charm. These are ITO nanocubes, and they have the resonance you see here around 3,000 wave numbers, so well in the infrared. And the enhancement of light absorption makes it possible to spot the vibrational transitions of the monolayer of molecules that sit on the plasmonic nanocubes. Okay, so this is something that you would not be able to see without plasmon resonance enhanced absorption. Okay, so this is something that's been discussed just since a few years. It looks very promising, but there are not many developments so far. The other thing that you can do is if you have a plasmonic material close to a chiral molecule, you can increase the CD signal, so the chiroptical signal, the circular dichroism response of these chiral molecules. So you stick a chiral molecule close to a plasmonic system, you have more light absorption, and so you have also more differential absorption, which is dichroism. Okay, this works for natural dichroism and also for magnetic circular dichroism. This is a paper we published a few years ago in which we placed a thin film of magnetic molecules, terbium bisphthalocyanine. This is a single molecule magnet. We placed it on top of plasmonic nanoantennas made of gold on a glass substrate, and we could see that there is a rather strong enhancement of the magneto-optical response of these molecules when we have the plasmon resonance overlapping the optical absorption of the molecule. Okay, so this is an interesting thing. So we went, we still haven't published this, but we went further into optimizing this process, and now we can spot monolayers of these molecules with magneto-optics, thanks to plasmon enhanced effects. Okay. Okay. Finally, metamaterials. I don't know if any of you have heard of metamaterials. These are rather fancy. It's like a buzzword now, but it's actually metamaterials are materials that show optical properties that do not exist in nature. Okay, they have been around since quite a few years in the microwave regime, and they've been using mostly as cloaking systems against radar. Okay, but so they present several potential optical benefits or gimmicks. One is negative refraction. So the metamaterials can, in principle, give you this kind of perception. With positive refraction of materials, light goes like this, travels in this way when going through a medium with lower refractive index to one with higher refractive index. And so you perceive objects in the water as in a different position. We all know this, okay? It's intuitive, okay? What if we switch to negative refraction? In this case, you see that the angle with which light travels in the higher refractive index medium, with the negative refractive index medium, is this. And this means that you will see this the fish as if it were floating out of the water. Okay, so this is a rather interesting thing. You can also think of cloaking devices, so objects, materials that will let light pass unaltered through an object. Well, not through, around an object. Okay, so this is a regular object. These are the fringes of the electromagnetic field of light. And in this case, you see the object, of course, interacts with light, and you won't have any light behind it. And that's how we see objects. So metamaterials can, in principle, give you this kind of behavior. So light curves around the object, and so it leaves the object unaltered. Okay, and all these properties can, in principle, be obtained with plasmonic materials if you're able to place many plasmonic objects in a very specific way, with a specific pattern, okay? And this is, for instance, a nice example, a metamaterial that can work as flat lenses is shown here. So you know, a lens, a classical lens has a certain thickness, okay, which is of the order of centimeters usually, or millimeters, okay? And usually you need a lot of lenses to correct aberrations and all that. You know that our smartphones, I always go back to the smartphone, but okay. So actually the current thickness of smartphones is not determined by the battery, by the processor, by whatever. It's determined by the optical assembly you see here of our cameras, okay? So there's all these lenses in here. And this takes up a certain slab of space. So meta lenses, so metamaterials with meta lens properties, are able in principle to do the same thing as a classical lens, but in a few nanometers of thickness. Okay, so you see here a meta lens. The designs look like this, okay, with electron microscope. But the blue part here is glass. It's not interacting with light actively. It's just these few nanometers of nanostructures that do the trick. So this is in principle very, very interesting. Okay, I think I will just skip these other applications, which are probably, okay, no, this one is interesting, but I'm running out of time. So enhanced absorption is very important in principle, not just for spectroscopy, but also for plasmonic solar cells. So as you know, in a solar cell, you're trying very hard to take light, to make light from the sun, to interact with material, with the active part of the material, of the solar cell, and convert this light into electricity, okay? So if you mix your light absorber with a plasmonic material, then you're going to have enhanced absorption of light, and so the efficiency with which you can trap light increases, okay? Finally, a very quick other concept, you can use plasmon resonance, so the absorption of light caused by plasmon resonance, and convert it into heat. So this can be used for several things. You can do some nice tricks. Like printing the nanoparticles on a substrate and then using infrared light to make them locally heat. These are ITO nanoparticles. This is something we did. Or you can do more serious things like trying to use local heating induced by infrared light to kill tumors. Okay, so this is called hyperthermia, optical hyperthermia. So these are all very interesting prospective applications. Okay, so just a few minutes for active plasmonics. So the idea behind active plasmonics is that we want to change the position of the resonance, of the plasmon resonance, using some kind of stimulus. Why do we need this? Well, there can be several reasons, but since we spoke a little bit about sensing, I'm going to give you the point of view of sensing, why it's interesting for sensing. So we said that in refractometric sensing, we want to see a small variation of the position of this peak as the molecule sticks to the plasma, to the plasmonic material, okay? So your limiting factor will be how good you are at seeing a very small shift of this plasmon resonance. And this gives, it can be related to a very general concept of measurement theory, which is this. So suppose you're looking for your friend here in this crowd of people, everyone's moving, shouting, and doing their thing. It's going to be difficult, you know, to find that specific person. But now suppose that you make everyone stand still and silent, and just your friend is waving at you at a certain frequency. So this is going to be much easier to see, okay? This is called signal modulation. It's kind of an encoding of a signal at a certain frequency, so you can retrieve just that portion of the signal that changes at a certain frequency. So the idea is we need to find a way to make the plasmon oscillate around a position and then sync to that frequency of oscillation so that we can selectively monitor changes in the plasmon resonance, okay? And this can be, this is called active plasmonics, and the stimulus can be electric field, magnetic field, temperature, chemistry, or even light, okay? I'm just going to give you a very, very brief overview of the possibilities. There's this very nice review that gives a much more in-depth overview of this. So you can just control the refractive index of your medium around the nanoparticle. So you change the dielectric properties of the medium, and this will change the position of the plasmon resonance. Or you can have a dimer of nanoparticles and change the distance, as I showed you in that example of the two nanorods that are linked by a DNA strand. Finally, you can control the carrier density. So if you can do this dynamically, so you inject or remove electrons from your plasmonic system, then you can change the resonant conditions. These are all active plasmonic examples. This one is also nice. You have this grain of iron oxide, which is magnetic, with some gold nanorods attached to them. As I told you before, the nanorod has two different resonances. So you can turn on the magnetic field. These magnetic rice grains will orient themselves with the field, and this means that also the gold nanorods will orient. And so you can select which plasmon resonance you want to see, the longitudinal or the transversal one, by changing the magnetic field. This is not magnetoplasmonics though. Magnetoplasmonics is this. And I'm going to have to be very, very quick because time is really finished. But so basically what happens is when you have a plasmon resonance, you have electrons moving. When you have electron moving in a magnetic field, these electrons will be will feel the magnetic field according to the Lorentz force, okay? So they will be deflected in a way. If you adjust the conditions of illumination and magnetic field and their relative orientations, what you can do is that you can shift the plasmon resonance with the field to lower or higher wavelengths, okay? So if you take an experiment in which you change the magnetic field from positive to negative, then you can move back and forth your plasmon resonance, okay? If you measure the difference between these two split peaks, you will get this kind of signal, okay? It's kind of a derivative of the optical peak. Now look at this. You remember we talked about SPR, okay? So this is the reflectogram, so how light is reflected off a plasmonic surface. And look at here at the shape of the magneto-optical response of plasmon resonances in a magnetic field. Okay, so you switch from a plasmon resonance, which is a peak, to a derivative. So at this point, the maximum of the plasmon resonance is not a peak anymore, but it's a very steep slope that gives you a stronger sensitivity to changes in the plasmon resonance position, okay? And this works on simple gold nanoparticles, okay? So the idea is that we want to increase how much the magnetic field splits these plasmon modes, which in turn makes this signal bigger and so it's going to be more sensitive because the signal-to-noise ratio is going to increase. So there are several strategies. A lot of work has been done on ferromagnetic plasmonic systems. For instance, nickel is the only ferromagnetic metal that can be made into nanostructures which have a plasmon resonance. So this is a very good idea. And this has also been proposed as a refractometric sensor with increased sensitivity thanks to this magnetic modulation. But there's a big drawback that the nickel discs are very magnetic, so they respond strongly to the magnetic field. But unfortunately, they have very broad plasmon resonance, and this is terrible in terms of sensitivity. Okay, so what we propose here is to use heavily doped semiconductors. Okay, so indium tin oxide nanoparticles, for instance, with a resonance in the infrared, and use these as magnetoplasmonic systems. Why is this? Because the amount of field-dependent plasmon modulation depends on these quantities here: the applied magnetic field, the electron charge, and the effective mass of electrons. Okay. So for most metals, the effective mass of electrons is the same of the real mass of the electron. But for heavily doped semiconductors, this is usually smaller. Okay, so this means that if you apply 1 Tesla of field to gold nanoparticles, you will have a certain shift. But if you apply the same 1 Tesla of field to ITO nanoparticles, you will have a much stronger effect because M is smaller. Okay, and this you can see here from the magneto-optical response of gold nanodiscs and indium tin oxide nanoparticles. You see that the magneto-optical signal is much bigger, and these systems are still non-magnetic. So this is a very important thing. The other very important thing is that plasmon resonances of ITO nanoparticles are very, very sharp compared also to gold. And this further increases the sensitivity with which we can detect refractometrics in refractometric sensing experiments. Okay. Okay, so just to conclude, we tried, the refractometric sensing experiment with ITO and fluoride indium doped cadmium oxide, another heavily doped semiconductor, and we found a better sensing sensitivity, okay, compared to all other magnetoplasmonic samples systems in the literature today. So this is a very good starting point, and it can also be made better if we add magnetic doping to these already doped systems, so that the field modulation will be even stronger. But this is something we will do in the future. Okay, so this is it. Sorry for being a little bit long, and thank you for your attention.
Okay, thank you very much, Francesco, for this wonderful talk, introductive and also very inspiring. Lots of science, many applications into it. So I saw there are several people with a question. So I would like to give you the opportunity to speak for yourself. So Beatrice.
Hi. Well, thank you for your presentation, because this field is very unknown to me, so it's very insightful, like Bruna say in the chat. So I have a few questions. They are all really simple, so I think it's be quick. My first was about solar cells, but you already answered in some applications. The second, if you have you talk a lot about inorganic materials, but you have some application to organic materials using semiconductors that are doped too. If you can use for do these enhancements that you talk.
Okay. So let me see if I understood your question. You're asking if organic semiconductors can be used as plasmonic substrates. Yeah, that's actually a very good question, and the answer is yes. Basically, there are some organic conductors, in fact. So these are conjugated systems usually that have been demonstrated to support plasmon resonance, and some groups did that, and that was a big deal because it was something that we just I mean, I had the same thought as you had, but somebody did that, so it was a very nice thing. Okay, just proof of concept. I have not seen applications based on this yet, but there might be in the future. Yeah.
Okay. My second question is about: is common to do theoretical calculations for predicted plasmons? If yes, what type of theory? You can use DFT normally, or is something new that you have to development to do this?
Sorry, theoretical calculation to predict what? The optical response?
Yeah, the optical response and the shifts and the.
Okay, so for very simple systems, you can just use the models that are close to Mie theory and all that. These are the so-called analytical models, so they're exact. You have one equation, you solve it. For all other cases, people use finite element methods. So these are methods, they're classical, right? They're not DFT, nothing like that, but they just take the geometry. So you draw your geometry of a system with the metal, the dielectric, the substrate, whatever, and then you make it interact with light. But what happens is that the geometry is decomposed into finite elements, okay? So into discrete systems. And then the algorithm basically calculate the response of every single piece of this workspace related to light, but also to the response of the neighboring discrete elements. And there are several of these. The simplest is discrete dipolar approximation, but then there are many other finite element methods. These are all classical, though. Yeah.
Okay. Okay, thank you.
Anderson.
Hi, Professor Francesco. Can you hear me?
Yeah, we can.
I understand.
Oh, okay, amazing. First of all, congrats for your presentation. It was really, really interesting. And I got a little bit curious about the use of plasmons as biochemical sensing. I would like to know if is it possible to use them to detect tumors or something like that.
Well, yeah, sure. Okay, if we go a little bit into analytical chemistry, so the plasmon resonance-based systems are part of the transduction. Okay, so the part that lets you observe an event. Okay, this said, once you functionalize the surface of your sensor with receptors that are specific to basically any biomolecule, you can use it for that purpose. So there are a lot of examples in the literature of selective sensor for markers, okay, so tumor markers. Another important technique related to plasmon resonance for the detection of these trace molecules is surface enhanced Raman scattering. That also is has been proposed a lot for the early, monitoring detection of. Yeah.
I see. Thank you.
Sure.
Thank you, Anderson. Fabio. Well, I will translate these questions. Yeah, he is asking how can the nanoplasmonics improve and contribute to NMR investigations, if it's possible.
Okay. Well, as far as I know, I'm not really expert in this, but while magnetic nanoparticles play really a very important role in magnetic resonance as negative contrast agents, I don't know of any use of plasmonic nanoparticles for as constant contrast agents for magnetic resonance. But this doesn't mean that they don't exist. They might exist, and I don't know of that. So yeah, no, basically they're not used very much for magnetic resonance. They are used as contrast agents in probably one of the few slides that I skipped. And let me go back to it very quickly because it's a nice picture. So. Okay, so here you can see it, right?
Yeah.
Okay. So the pictures you see here at the bottom are optical microscopy pictures, and here they label certain cells with gold nanoparticles. In this case, they have an optical contrast agent. Okay, in this case, gold nanoparticles behave as strong light scatters. And so you see a lot of light going back into the microscope, CCD or optics. Okay, yeah. So this is in optical microscopy, not in magnetic resonance, as far as I know. Only magnetic nanoparticles are being used as contrast agents in magnetic resonance.
Oh, thank you. Then we have another one from the Fabio as well, and there's also I would like to. I have a doubt about how do you believe the quantum tunneling can be used in nanoplasmonics research, and does it appear somehow somewhere, and has that been investigated? Because since you told us that this effect can be found in molecules. Before Beatrice was asking a question which was smarter than mine, because I will wanted to ask you, is it possible, do you believe it's possible to create the molecular environment able to produce a plasmonic effect in a molecular entity? And that was my original question. And do you believe it's possible to use monodispersed molecules? With this, I wanted to say that not using nanoparticles of polymers. That do you believe we can do it in discrete molecules? And in this case, it's going to is it possible to be seen any quantum tunneling effect related to this?
Okay. Lots of parts of this question, which is very interesting. But so, first of all, you mean tunneling of charges? Okay, so so these are two aspects that are a bit different. So I will try to go through the molecule thing first. So it's very fascinating that the transition between plasmon resonances and single electron transitions is not really completely clear. Okay, so in my opinion, the best system to consider, so it's a bit different from what you were thinking about molecules, but it's a very nice thing. If you take molecular clusters of gold, for instance, so there are some clusters that can be prepared stoichiometrically, gold 25, these magic number clusters. These are actually molecules. You can crystallize them, you can have the structure, and they do have a spectrum which has no plasmon, but has transitions, optical transitions, okay? Then just a few atoms later, you get a plasmon resonance, which is very broad, not very easy to observe, but there is indeed a point in which you have this transition. I don't know how well this has been studied, but I think that's the most interesting point. Then, if you really want instead a molecular entity with a lot of free electrons that is still a molecule, so not a polymer nanoparticle, that, as far as I know, has never been done. Okay, the closest thing is these gold clusters, but it's a bit of a different thing. Instead, quantum tunneling. So there is a very, very nice research area in theory of plasmonics, mostly done by Garcia de Abajo, who's a very, very talented theoretician in Spain, in which they take two nanoparticles and they make them get closer and closer. So they close the gap, and they see that at a certain point, if you use a classical model, the response is different, very different from the experimental one. So they actually do the experiment. And at that point, they must invoke quantum tunneling between the two particles for that. So yes, it does, it comes into place. It has been rationalized, and it has been also, I mean, understanding and being able to quantify these effects, of course, brings in a new new momentum to research in these hotspots, because of course then you can really design a hotspot for a certain molecule that will be extremely efficient. So yeah, it's a very important thing.
Oh, thank you. Yeah, it's very interesting. They should apply the magnetic field to see what happens on the dimer of the nanoparticles. So, Gabriel?
Hello, can you hear me?
Yeah.
Yeah.
Thank you very much for the talk. Really like the presentation.
Thank you.
There was a slide where you showed us a wearable application. And the first thing that came to my mind was graphene. Can we use graphene in the plasmonic field?
That's a very, very good question. Yeah, they did. And they published a lot of very, very high impact papers on that. Plasmonics in graphene is a hot topic. The thing is that you remember I told you that the position, the spectral position of the plasmon depends on electron density. Okay, so this means that the natural resonance position of the plasmon in graphene is in the far, far infrared, in the terahertz regime, in fact. But it's there. And it's very interesting because graphene can be gated through electrical contacts, and you can inject charge and get it in and out. So you can move the plasmon resonance a lot. a lot in spectral position, and this is very important. And the other thing is that for the particular band structure of electronic band structure of graphene, electrons have a very small mass, effective mass, so they will also respond to magnetic field very strongly. Yeah, so yeah, it's been done. The first observation were done by SNOM, so a scanning tunneling optical microscopy. I think the first observation, not really sure, but among the first in Nanogune in San Sebastian in Spain, with this local optical microscopy. Very nice experiment.
Thank you.
Impressive. Beatriz?
Hey, I have another question because you were talking about the tunneling quantum, so I think of one thing. Do you know what is phonon? Phonon is the vibration of crystal.
Mm-hmm.
Yeah. Have some research about the coupling plasmons and phonons. If you have, what to do with this information?
Okay. Yeah, this is also a very nice topic. Well, if in first I will give you a molecular analogy, because of course a phonon, if you take the phonon to the molecule world, it's a vibrational transition. Okay, so in this case, the surface enhanced infrared absorption is one example of interaction between plasmons and phonons. But in this case, the two things behave as different things. There are some mixed mode phonon polariton modes. So these are propagating plasmons that couple also to phonon in crystals. They have been studied. I must say I don't know very much about them, but I think they have just, been treated theoretically, observed. I don't know of any use that has been made with them. So yeah, this is.
Okay, thank you.
Okay, in principle, we should have get over with all of our questions, but I have a couple more. Sorry for you guys. Looks like the people from the YouTube channel didn't have any question. So I have a couple of doubts. The first of all has there anyone studied the time dependence of the excitation of the plasma? I mean, you showed us every experiment is with a continuous light irradiation. Is there a time dependence of the plasmonic oscillations? And is this relevant? No.
No. Okay. No, of course, the answer is yes to both questions. They have been studied. Of course, the time, typical lifetime of a plasmon resonance is related basically to the width of the resonance. Okay, as any resonator. So since the natural wave width of the resonance is much bigger than that than that of molecules. In fact, it's tens of nanometers. In fact, they're very short-lived excitations. They're very short-lived, and this has been studied. There have been mostly, I must say, for the research theme of hot electrons. So once hot electrons is a very important thing of the field of plasmonics. I didn't think of including it in today's presentation, but it's it consists in this. You excite a plasmon, you have this population of electrons that are in an excited state in the metal, and these can be used by other molecules to for instance induce photochemical reactions or things like that. And in that case, of course, the lifetime is very important, because you need to know how much time you have to capture this energy before it goes away. But yeah, usually it's done by pump and probe experiments. So classical pump and probe experiments. And sorry, the other nice thing is that, for instance, in semiconductors, you can transiently populate the empty conduction band with a very strong pulse. So you populate the band and you have a transient plasmon that lives as far as, well, no, that can be excited as far as you have this population on in the excited state. That's nice.
And you change the frequency and the energy and intensity of the plasma like this.
Yeah, yeah. It's one of the active plasmonic approaches that.
And which is the relative intensity of this vanishing plasmon with the original one?
Well, I mean, if you take, you mean in this the last case now that I just said?
Yeah.
Well, in principle, if you take a normal semiconductor not doped, you have no plasmon without excitation.
Okay, yeah.
But then it really depends on how many electrons you can put into the, how much you can populate the band.
It can be seen anyway.
It can be seen, and at that point, it really depends. The position depends on electron both position and intensity depend on electron density. So, in principle, the more efficiently you can populate the conduction band, the more intense and the more blue shifted will be your plasmon.
Thank you. Last one. When you showed us the magnetoplasmonics of the gold nanoparticles, you showed a delta A formula, and the delta A formula, you introduced the effective mass of the electron there. But that delta A formula is very similar to the Zeeman effect in molecular materials. And the same formula is basically the Bohr magneton, the one you're reporting there. So is there any relation? The only thing that's missing is the spin of the value of the spin. It looks to me that the value of the spin is included in the reduced mass. So is there any, because the spin may vary between 1/2 to 7/2, no? And this leads to an increase in the delta A separation, in the Zeeman separation. You say that the delta A separation is increasing because it's decreasing the electron mass at the denominator. Is there any relation between these two things? I mean, the Zeeman effect and the apparent mass of the electron.
Well, this is a very good question, but I don't think I know the answer. So the effective mass in a solid is in fact the result of all the potentials that are within the lattice that then determine how the electron
nothing
responds.
To do with the spins in principle.
In principle, no. And in fact, but the analogy, of course, is there, and so that quantity is classically called cyclotron frequency, and it's called like this because, in fact, in cyclotrons, which are these devices in which you have free electrons moving in a magnetic field, the frequency with which they spin around is determined by those quantities. But yeah, no, I'm not aware of a direct relation in this case between M and spins, but it's something that I should probably think about, because I don't really think it's totally unrelated, because I mean, that's
the formula, it's very similar.
Yeah. It's really similar.
Okay, so thank you very much So people, please, let's open, as we do at the end of our seminars, our microphones, and if you want cameras, to thank Professor Francesco again for this very nice talk and very, very interesting conversation we had. So thank you.
Bravo.
Thank you. Thank you all for your attention and nice questions.
And okay, so thank you very much, and see we will see Francesco somewhere in a different occasion, I hope, and see all of you in a couple of weeks, guys. Have a nice day.
Okay, bye. Thank you.
Bye. Have a nice day.
Grazie, grazie.